Deep in the silent reaches of space, stars live, burn, and die on timescales that dwarf human history. Most end their lives quietly, fading into white dwarfs or collapsing into black holes without ever threatening us. But a few die violently, so violently that their deaths can be felt across galaxies. These are supernovae, cosmic detonations so powerful they can outshine the combined light of billions of stars. And somewhere, perhaps closer than we dare imagine, one of these ticking bombs is waiting for its moment. Astronomers tell us that if such an explosion happened close enough to Earth, the results would be catastrophic. But how close is close enough? What would we see? What would we feel? And the most unsettling question, would we even have time to prepare? Today, we're going to explore what would happen if a star exploded right next to Earth, not in cosmic terms of next door, meaning light years away, but truly close. We'll peel back the layers of science and possibility, moving from the first eerie warning signs to the long-term transformation of our planet. And along the way, we'll uncover a startling truth. The end of a star is not simply a blast. It's a chain reaction that can reshape entire solar systems, and perhaps the history of life itself. Before we can imagine the disaster, we need to understand the monster. A supernova occurs when a massive star, at least 8 times the mass of our Sun, exhausts the nuclear fuel in its core. Without the outward pressure of fusion to counter gravity, the core collapses in milliseconds. The result? An implosion followed by an explosion of unimaginable force. In a core collapse supernova, the collapsing core rebounds, sending shockwaves ripping through the star's outer layers. In a Type Ia supernova, a white dwarf steals matter from a companion until it ignites in a thermonuclear runaway. In both cases, the energy released in seconds can equal the total output of our Sun over its entire 10 billion year lifetime. And that's when the fireworks begin. The blast hurls stellar matter into space at thousands of kilometers per second. Radiation floods the surrounding region. Neutrinos, ghostly particles that barely interact with matter, stream out in numbers so vast that in the first seconds, more neutrinos pass through your body than there are atoms in the Sun. From light years away, this is a spectacular but harmless show. But what happens when the star is not light years away, but fractions of a light year? In astrophysics, distances are deceptive. Nearby can mean many things. The rule of thumb is that if a supernova occurs within about 30 light years of Earth, its radiation can damage our ozone layer, exposing life to lethal levels of ultraviolet light. Within 10 light years, the effects become far more severe. Mass extinctions are possible. At 1 light year or less, the energy influx would be unlike anything life on Earth has ever faced. And if the exploding star were within the outer reaches of our own solar system, say, in the Oort cloud, we wouldn't just be talking about environmental damage. We'd be talking about the survival of the planet itself. Contrary to Hollywood portrayals, the first sign of an impending nearby supernova wouldn't be a sudden flash in the sky. The earliest warning would be invisible, a surge of neutrinos arriving hours before the light. These particles would race ahead, traveling unhindered through space and Earth alike. Only specialized detectors, massive underground tanks of ultra-pure water would notice them. To the public, the first visible clue would be subtle. The star in question, perhaps a familiar point of light in the night sky, would begin to brighten over days or weeks. Amateur astronomers might notice first, posting strange observations online. Then, as the explosion's shockwave reached the stellar surface, the star would brighten by millions of times in a single instant. Night would turn to day across half the Earth. If the exploding star were close enough, the initial burst of high-energy gamma rays could be devastating all by itself. Gamma-ray photons carry so much energy that they can break molecular bonds in our atmosphere, leading to a chemical chain reaction that strips away the ozone layer. Without that shield, the Sun's ultraviolet radiation would bombard the surface, sterilizing unprotected land and shallow ocean layers. The burst could last seconds to minutes, but the damage would last decades. Then comes the blast wave, a sphere of superheated plasma and stellar debris racing outward at a fraction of light speed. In deep space, this shockwave is mostly empty, expanding into vacuum. But at extreme proximity, it carries enough mass and momentum to physically batter planets. If Earth lay inside the innermost danger zone, say, within a few 100 billion kilometers, the wave would slam into our magnetosphere and atmosphere with unimaginable violence. The upper atmosphere would superheat. Auroras would blaze at every latitude, the sky shimmering with ghostly curtains of green and red. Satellites would fry instantly. The ISS would be stripped to fragments. But this is only the beginning. Even if Earth somehow remained intact, the explosion would dump colossal amounts of energy into our planet's systems. Climate would swing wildly. The biosphere, already reeling from radiation damage, would face decades, perhaps centuries of unstable conditions. And here's where the story takes a turn. The geological record shows patterns, sudden shifts in climate, mysterious extinction events, and isotope anomalies that some scientists have linked to nearby supernovae in Earth's past. If it has happened before, it could happen again. If the idea of a nearby star exploding sounds like pure science fiction, the unsettling truth is this: Earth may have already lived through such an event. Our planet's geological memory is imperfect erosion, plate tectonics, and biological activity erase most traces over millions of years. But in the last few decades, scientists have learned to read the faint fingerprints left behind by cosmic cataclysms. These fingerprints don't appear as giant craters or charred landscapes. Instead, they are scattered isotopes, subtle chemical shifts, and microscopic clues buried in ancient sediments and ice cores. They tell the story of events so immense that they could only have originated beyond our solar system. In 1999, researchers analyzing deep-sea ferromanganese crusts, slow-growing mineral layers that record millions of years of history, discovered something strange: an unusual concentration of iron-60. This isotope doesn't occur naturally in significant amounts on Earth because it decays with a half-life of just 2.6 million years. So, where did it come from? Iron-60 is forged in the nuclear furnaces of massive stars and scattered into space by supernova explosions. Its sudden appearance in Earth's geological record, dated to around 2-3 million years ago, points to a nearby stellar death. Later, in 2016, scientists found more of this cosmic isotope in Antarctic snow freshly fallen, meaning it's still drifting through our solar system today from ancient explosions. These particles are messengers from a star that died within about 100 light-years of us, sometime in the not-too-distant past on geological timescales. The timing of this ancient supernova aligns eerily with the dawn of the Pleistocene epoch, the period when Earth entered a cycle of repeated ice ages. Was that timing a coincidence? Or did the supernova's blast play a role in reshaping our climate? One hypothesis suggests that the influx of cosmic rays from the explosion could have altered cloud formation, triggering cooling trends that locked Earth into a new climate rhythm. If so, our Ice Age landscapes and even the evolutionary pressures that shaped early humans might trace their origins to the death of a distant star. The iron-60 layers in our crust don't tell a story of a single explosion. Instead, they appear in distinct bands, separated by hundreds of thousands of years. This suggests that Earth may have been hit by the debris of multiple nearby supernovae, perhaps from stars belonging to the same stellar association passing close to the Sun. The prime suspect? The Scorpius-Centaurus OB Association, a loose cluster of young, massive stars located a few hundred light-years away. Over millions of years, these giants have been burning fast, dying young, and exploding in a chain reaction of stellar deaths. One reason we might overlook the danger of nearby supernovae is that they're quiet until they're not. Unlike asteroid impacts, which come with visible, trackable objects hurtling toward us, the precursors of supernovae can lurk in the background of the night sky for millions of years, blending in with ordinary stars. The warning signs are subtle: a change in spectral lines, an unexpected dimming or brightening, or unusual neutrino emissions. But unless astronomers are watching the right star at the right time, we might have no advance notice at all. Geologists and astronomers have now teamed up to develop what's essentially cosmic crime scene investigation. They look for isotopes like iron-60, plutonium-244, and manganese-53, all radioactive elements with lifespans short enough that their presence on Earth can only be explained by recent stellar events. These isotopes have been found not just in ocean sediments, but also in lunar soil collected by the Apollo missions. The moon's surface, lacking an atmosphere, acts as a pristine record of whatever the cosmos throws at us. Its regolith carries the same Iron 60 signature as Earth, confirming that the entire solar system passed through the supernova's fallout cloud. Understanding that nearby supernovae have occurred before and that Earth has survived might be comforting. But the survival of life in the past doesn't guarantee our safety in the future. Our technological civilization is fragile in ways nature is not. A burst of radiation strong enough to slightly damage the ozone layer for prehistoric animals could obliterate modern satellite networks, fry electrical grids, and disrupt the digital backbone that holds our societies together. The margin between inconvenience and collapse is far smaller for us than for early mammals or fish. When most people hear the word supernova, they imagine a single type of event, a star simply detonating like a cosmic bomb. In reality, there's a whole spectrum of stellar deaths, each with its own signature and level of danger. Some are relatively benign, unless they happen in our galactic backyard. Others are so extreme that they could wipe out life from thousands of light years away. The key variables are energy output, radiation type, and perhaps most crucially, directionality. Some stellar deaths unleash their fury in all directions equally. Others focus their energy into tight, blinding beams, cosmic sniper shots that can traverse the galaxy. These are the classic death throes of massive stars, anything over about 8 times the sun's mass. They end their lives when the nuclear fuel in their cores runs out, gravity wins, and the star's heart collapses in on itself. The collapsing core rebounds violently, blasting the star's outer layers into space at up to 10% the speed of light. In the first seconds, 99% of the event's energy escapes as neutrinos. These ghostly particles will pass right through you and through the entire planet without much effect. The danger comes from the accompanying electromagnetic radiation. Visible light, ultraviolet, X-rays, and, at very close distances, gamma rays. Within a 10 light-year radius, a core collapse supernova could severely damage Earth's atmosphere. But beyond 30 light-years, its radiation becomes less dangerous to life, though it could still light up the night sky for months. If core collapse supernovae are the deaths of massive stars, type Ia explosions are the deaths of dead stars. A white dwarf, the compact remnant of a sun-like star, pulls matter from a close companion until it exceeds a critical mass. At that point, runaway fusion ignites, and the entire star detonates in a thermonuclear explosion. These are standard candles for astronomers because they release a predictable amount of energy. But predictability doesn't mean harmless. A Type Ia supernova within 25 light-years could bathe Earth in enough gamma and X-ray radiation to destroy the ozone layer, triggering a cascade of environmental disasters. The unsettling part: white dwarfs are common. Some already have companions close enough for mass transfer, meaning the next Type Ia could be closer than we think. If supernovae are cosmic bombs, hypernovae are thermonuclear weapons on a galactic scale. These ultra-energetic explosions happen when the most massive stars, perhaps 30 times the sun's mass or more, collapse directly into black holes. The collapsing material forms an accretion disk around the newborn black hole, and in certain cases, it launches 2 narrow, oppositely directed jets at near light speed. These jets aren't just bright, they're loaded with gamma rays. A gamma ray burst, GRB, is arguably the most dangerous phenomenon known to life in the universe. Unlike the spherical blasts of most supernovae, GRBs concentrate much of their energy into beams just a few degrees wide. If one of those beams is pointed directly at you, distance becomes less of a comfort. Astronomers estimate that a GRB within 0 to 10 light-years aimed squarely at Earth could cause a mass extinction. The burst's gamma radiation would rip apart atmospheric molecules, creating nitric oxides that destroy ozone and darken the skies. It wouldn't be instant annihilation. Life would die more slowly, through ultraviolet bombardment from the sun, climate collapse, and ecological chain reactions. But for complex organisms, the end result would be the same. Some scientists believe that GRBs may have been responsible for certain unexplained mass extinction events in the fossil record. One leading candidate is the Ordovician Silurian extinction, around 450 million years ago, which wiped out roughly 85% of marine species. The pattern rapid die-off, followed by cooling fits, the ozone destruction and climate effects expected from a distant GRB. If true, it would mean that life on Earth has already faced the universe's most lethal weapon and survived, albeit barely. The good news is that GRBs are rare in our galaxy. The bad news is that rare isn't the same as never. Our Milky Way produces a few supernovae per century and perhaps a GRB every few million years. Over geological timescales, those odds aren't comforting. When you stretch the timeline to billions of years, the lifespan of complex life on a planet, the universe begins to look like a shooting range, and survival depends on where the crosshairs are pointing. In the vast darkness of space, a star's death cry begins in silence. Long before the visible explosion, long before the shockwave, the first signal that something is terribly wrong arrives in the form of particles we almost never notice. Neutrinos. Neutrinos are the universe's ultimate escape artists, nearly massless, electrically neutral, and able to pass through light years of solid lead without stopping. When a massive star's core collapses, it releases a flood of them. For a supernova in our galactic neighborhood, trillions of neutrinos would stream through every square centimeter of Earth's surface in just a few seconds. We wouldn't feel a thing. But deep underground, buried in old mines and under mountains, massive detectors filled with pure water or liquid scintillators would suddenly light up with ghostly flashes. To the scientists watching, this would be the cosmic equivalent of hearing a gun's safety click off. Right now, Earth's network of neutrino observatories, Super Kamiokande in Japan, IceCube in Antarctica, and others, is linked into an early warning system called SNEWS, the Supernova Early Warning System. If a nearby star's core collapsed tonight, SNEWS could detect the neutrino surge hours before the first photons reached us. Those hours might be all the lead time we'd get before the visible explosion and before the more dangerous radiation began arriving. In a best-case scenario, that warning could allow astronomers to train every telescope on the source, governments to alert power grids and satellite operators, and ordinary people to prepare for potential disruptions. In a worst-case scenario, if the star were very close, it would simply be a countdown to catastrophe. When the explosion's shockwave reaches the surface of the star, photons trapped inside for millennia are suddenly free. The result is a brief but blinding shock breakout, a surge of ultraviolet and X-ray light, followed by a massive increase in visible brightness. If the supernova were within a few dozen light years, it would become brighter than the full moon and visible even in daylight. For something uncomfortably close, a few light years or less, night across half the planet would turn into a strange, ghostly day. Shadows would appear where they had no business being, cast by a sun-like brightness in the wrong part of the sky. The real threat isn't the visible light, it's the high-energy photons riding along with it. X-rays and gamma rays have the power to ionize atmospheric molecules, triggering chain reactions that can strip away ozone and flood the surface with harmful ultraviolet light from our own sun. For a nearby supernova, this effect could last years. Even with partial ozone recovery, ecosystems would be thrown into chaos. The most sensitive species, plankton, amphibians, pollinating insects could collapse first, triggering food chain disruptions that ripple upward to larger animals, including us. Unlike an earthquake or hurricane, the effects of a nearby supernova wouldn't be confined to one region. The atmosphere is a global system. Damage in one hemisphere affects the entire planet. Agriculture would face reduced yields, altered rainfall patterns, and unpredictable growing seasons. The modern world's dense interconnection would turn local shortages into worldwide crises. We've seen how a few percentage points drop in grain harvests can destabilize markets. Now imagine that on every continent at once, under skies that are a little too bright at night and a little too dangerous during the day. For certain nearby stars, yes, Betelgeuse, for example, is already under constant watch. If it were about to explode, changes in its brightness, temperature, and spectrum could give us years or even decades of warning. But many stars don't advertise their instability so clearly. Some, especially white dwarfs heading toward a Type Ia supernova, could go critical without much visible sign until the very last moments. In those cases, our first and only warning would be that silent flood of neutrinos, hours before the light and radiation arrived. It's easy to focus on the physical effects, the heat, the light, the radiation, but the human mind is wired to find meaning in the sky. A second sun appearing suddenly in the night would not just be a scientific event, it would be a cultural shockwave. Religions, economies, and political systems have all been shaped by much smaller astronomical events, eclipses, comets, meteor showers. A visible, long-lasting supernova close enough to alter our environment would dominate every conversation, every news cycle, every work of art and story. In the past, supernovae have been recorded in ancient Chinese star catalogs, painted into medieval manuscripts, and carved into rock art. But humanity has never faced one that was too close. That would be a test of not just our technology, but our collective psychology. The instant the light and radiation arrive, the sky changes forever. If the supernova is close enough, the gamma ray and X-ray burst will slam into the upper atmosphere, knocking electrons off molecules and creating a sudden surge of ionization. The effect is invisible to the naked eye, but to our satellites, it's blinding. GPS signals distort, communication links flicker, and power grids feel the first tremors of instability. Within seconds, high-energy photons begin breaking apart oxygen molecules, forming ozone-destroying nitrogen oxides in massive quantities. As the ionization cascade continues, the atmosphere's chemistry shifts. The ozone layer, our shield against the sun's ultraviolet radiation, begins to thin. In normal conditions, ozone is constantly destroyed and regenerated, maintaining a delicate balance. The sudden influx of nitrogen oxides tips that balance hard toward destruction. Meanwhile, the upper atmosphere heats rapidly. This expansion changes the density profile of the air above us, altering how radio waves travel and causing long-distance communication blackouts. The auroras, already bright from the blast's charged particles, intensify into surreal curtains of red, green, and violet, visible even in daylight. By now, every life form on the sunlit side of Earth is being exposed to higher than normal ultraviolet radiation. For humans, the immediate danger is sunburn and eye damage. For phytoplankton, the microscopic plants at the base of the marine food chain, the effect is far worse. UV radiation penetrates the ocean's surface layers, damaging DNA and crippling photosynthesis. This isn't just an ecological problem, it's a planetary one. Phytoplankton produce a large fraction of Earth's oxygen and play a major role in carbon cycling. A collapse here is a domino that can topple entire climate systems. Ozone loss peaks within months, and the climate begins to wobble. Increased UV stress on plants reduces crop yields, while changes in atmospheric circulation shift rainfall patterns. Drought grips some regions, flooding hits others. The global food supply becomes unstable. The nitrogen oxides created in the initial burst have another effect. They eventually rain out as nitric acid, acidifying soils and freshwater ecosystems. Ancient tree rings from suspected past supernova events show growth anomalies, stunted rings in the years following, consistent with such acid rain events. Even if the ozone layer slowly recovers, the damage lingers. Ecosystems reorganize. Some species adapt or migrate, others vanish entirely. On land, UV-hardy plants and animals gain an advantage, reshaping entire biomes. In the ocean, shifts in plankton communities ripple up through fish populations, seabirds, and marine mammals. Human societies may recover technologically but remain permanently altered. Agriculture adapts with UV-resistant crops and indoor farming. Outdoor life changes. More shade, more protective clothing, a cultural shift toward living under cover. In extreme cases, entire cities might move partially underground or underwater to shield themselves from chronic radiation. In Earth's geological record, there are curious intervals where carbon isotopes, fossil assemblages, and trace metals all shift at once, but without the obvious markers of volcanic eruptions or asteroid impacts. One candidate is the Devonian extinction events around 360 million years ago. Fossils from this period show signs of UV stress, malformed spores in ancient plants, indicating a possible ozone collapse. While volcanic eruptions or other terrestrial processes could explain it, some scientists have wondered if a nearby supernova could fit the pattern, a sudden, global, radiation-induced environmental shift without an impact crater. If true, it would mean our planet has faced this invisible killer before, with consequences lasting millions of years. The sobering part is that the same chain of events could unfold today, but with a civilization far more vulnerable than any in the fossil record. Our food supply chains, power grids, and digital networks depend on a degree of environmental stability that nature doesn't promise. In deep time, life on Earth is adaptable. Civilizations are not. A supernova's atmospheric impact could push us into a survival mode, where maintaining global order becomes harder than surviving the physical disaster itself. The most violent moments of a nearby supernova would be over in hours. The gamma rays, the X-rays, the first electromagnetic shockwave. But the star's death wouldn't end with a single cosmic scream. It would leave a whisper that echoes for millennia, a steady rain of debris drifting through interstellar space toward our solar system. This debris isn't harmless dust. It carries the fingerprints of the star's final moments, isotopes forged in the explosion's furnace, particles traveling at thousands of kilometers per second, and grains of material capable of altering entire planetary environments. A supernova is nature's ultimate foundry. In the searing heat and pressure of its core collapse, atoms fuse into elements heavier than iron, gold, uranium, plutonium, materials that cannot be produced in ordinary stellar fusion. These newly minted elements are blasted outward into space, mixed with fragments of the star's outer layers. If the explosion happened within a few light years, some of this material would eventually cross the gap to Earth. It wouldn't arrive all at once. Instead, it would drift in over thousands of years, carried by the expanding shell of the supernova remnant. When this material reaches Earth, it would leave chemical markers in ice cores, sediments, and even lunar soil. We know this because we've already found them. Iron-60 from supernovae a few million years ago, plutonium-244 from older events, and manganese-53, all radioactive isotopes with no natural sources on our planet. A nearby future supernova could add a new layer to that isotopic record, one that future civilizations might discover long after we're gone. The presence of these elements would be unambiguous proof that we lived through the death of a star. But debris brings more than exotic isotopes. Supernovae eject vast clouds of fine dust, microscopic grains of carbon, silicates, and metal compounds. If enough of it reaches the inner solar system, it could scatter sunlight, cooling the planet in a phenomenon similar to a volcanic winter. Historical analogues hint at the consequences. After massive volcanic eruptions like Tambora in 1815, Earth experienced years without summer, crop failures, and famine. A supernova-induced dust veil could be longer lasting, with dust continuing to trickle in for decades or centuries, prolonging climatic instability. The debris cloud wouldn't be inert. Some grains would carry trapped radioactivity, continuing to emit ionizing radiation long after the blast. Most would burn harmlessly in the upper atmosphere, but the cumulative effect could subtly raise global background radiation levels for centuries. For a planet with complex electronics, there's another danger. Charged dust interacting with Earth's magnetic field could cause persistent auroras and geomagnetic disturbances, a kind of space weather drawn out for decades. Earth's atmosphere would shield us from most physical impacts, but the moon would take the debris unfiltered. Its surface, already an archive of cosmic history, would accumulate a distinct layer of supernova dust. Future lunar explorers could scoop up this layer and date the isotopes within it, pinpointing the exact century the blast occurred. It would be an eternal monument, sitting silent in the regolith, marking the time the sky burned brighter than the sun. Supernova debris doesn't just affect planets, it changes the space environment itself. As the debris wave sweeps through the solar system, it could sandblast satellites, cloud orbital paths, and increase collision risks. In extreme cases, fine dust particles moving at tens of kilometers per second could damage spacecraft even in deep space. For decades after the event, interplanetary travel would mean navigating through a shooting gallery of microscopic bullets. The idea that supernova debris could alter planetary environments for centuries or millennia may explain certain puzzling intervals in the geological record. Periods of gradual climate cooling, elevated cosmic ray levels, and odd isotope concentrations all without obvious volcanic or impact triggers. Such patterns may not mark a single catastrophic moment, but the long tail of a cosmic disaster, the drawn-out influence of a star that died within sight of our ancestors. Once the debris arrives, there is no stopping it. Space is vast, but in the wake of a nearby supernova, the solar system becomes like a pond after a rock has been thrown in. Waves of matter and energy ripple outward, impossible to reverse, only to be endured. This isn't the sharp, clean blow of an asteroid impact. It's the slow suffocation of a changing environment, the gradual rewriting of climate, chemistry, and habitability. A supernova close enough to harm Earth would not spare our neighbors. The blast's radiation, debris, and shockwave would wash over every world in the solar system, reshaping them in different ways depending on their atmospheres, surfaces, and magnetic fields. In the weeks and centuries that follow, the solar system would become a gallery of transformation and devastation. Closest to the Sun and lacking any significant atmosphere, Mercury would take the supernova's radiation directly, its surface heating unevenly under the barrage of high-energy photons. The lack of air means no chemical protection. The star's X-rays and gamma rays would bake its regolith, altering the chemistry of its surface minerals. Mercury would be little changed visually, but its top layer would become a frozen record of the event. Shrouded in thick clouds of carbon dioxide and sulfuric acid, Venus might seem well shielded, and to a degree, it is. But high-energy radiation could trigger new chemical reactions in its upper atmosphere, creating temporary compounds and possibly altering its already reflective cloud cover. The effects might be subtle compared to Earth's, but they could change how Venus traps heat, at least for a few decades. Mars has only a thin atmosphere and a weak magnetic field, making it extremely vulnerable. The supernova's radiation and charged particle storm could strip away a measurable fraction of its atmosphere, a process similar to how solar wind has eroded it over eons, only far more intense and rapid. For future Mars colonies, the event would be devastating. Any unshielded habitat would be blasted with lethal radiation. Surface rovers, satellites, and communication systems would be knocked out by the electrical chaos in the upper atmosphere. The rocky debris between Mars and Jupiter would light up under the impact of high-energy particles, releasing gases from volatile-rich asteroids. Dust clouds stirred up by micro-collisions could linger, slightly increasing the density of material in the belt and posing navigation hazards for spacecraft. Jupiter's massive magnetic field would interact spectacularly with the incoming charged particles, producing auroras brighter and more widespread than any in recorded history. The planet's radiation belts, already deadly to spacecraft, would be supercharged, making exploration impossible for years. Its thick atmosphere would absorb most of the energy, but changes in cloud chemistry might be detectable for decades afterward, an alien weather report in the making. Saturn's iconic rings would become a cosmic display screen, scattering the supernova's light into strange, shifting patterns visible across millions of kilometers. Dust and debris from the blast could be captured by the rings, altering their composition and brightness. Some fine particles might even be driven into Saturn's atmosphere, producing temporary streaks of unusual coloration. Moons like Europa, Enceladus, and Titan would experience more dramatic effects. Radiation could break apart surface ice molecules, releasing plumes of gas and altering their chemical makeup. For Titan, with its thick nitrogen atmosphere, the chemistry of its methane clouds could shift dramatically, producing a brief but detectable change in its orange haze. Farther out, the ice giants would quietly soak up the supernova's radiation. Their deep atmospheres and great distances would shield them from the most immediate damage, but their upper layers might still see changes in chemistry. In the thin sunlight of their orbits, the supernova's flash could briefly outshine the sun itself. On the outer edge of the solar system, the blast wave would sweep through the Kuiper Belt, rattling dwarf planets and icy bodies. Many of these small worlds would lose surface volatiles as radiation sublimated their ices, producing short-lived comas like comets. Even farther, in the Oort cloud, a shell of icy bodies stretching halfway to the nearest stars, the shock could destabilize orbits, sending comets inward toward the sun in a delayed barrage that might last for centuries. From the innermost rock to the most distant icy fragments, every body in the solar system would carry scars of the supernova. Some would be chemical altered molecules and isotopes. Others would be mechanical new craters from debris collisions or changes in ring structure. If intelligent life returned to the solar system millions of years later, these scars would be clues, a breadcrumb trail leading to the conclusion that once, here, a nearby star had died and its death had touched every world. A supernova's blast is not just light and radiation, it's a sphere of expanding, superheated gas and plasma sweeping outward through the galaxy. Even hundreds of thousands of years after the initial detonation, this shockwave can still be traveling at thousands of kilometers per second, plowing through the thin interstellar medium like a snowplow through powder. Within a few light years, the effect is devastating. The shock strips gas and dust from anything in its path, sweeping clean entire regions of space. Farther out, the wave loses energy, but still perturbs delicate cosmic structures, comet clouds, dust lanes, and even the wispy material that will one day become stars and planets. In our cosmic neighborhood, stars are separated by only a few light years on average. If the exploding star is close enough to us to be dangerous, it's close enough to be dangerous to others. Any planetary systems within a 1030 light-year sphere could face similar ozone destruction, climate chaos, and mass extinctions. Some might fare better than Earth, protected by thicker atmospheres or more distant orbits from their stars. Others could be sterilized entirely. The blast's reach is democratic. It doesn't care about life, technology, or history. One of the more subtle and longer-term dangers comes from gravitational nudges. Our own Oort cloud is a loose, fragile shell of icy bodies extending light years from the sun. A supernova's shockwave can pass through it, ever so slightly altering the orbits of countless comets. Some will be nudged toward the inner solar system, beginning a centuries-long reign of impact. The same would happen to other stars' comet clouds, potentially creating a cascade of delayed disasters across multiple systems. A planet that survives the radiation storm might still face a slow-motion extinction centuries later. Ironically, supernovae are also engines of creation. Their shockwaves can compress clouds of interstellar gas, triggering the collapse of regions that have been floating quietly for millions of years. In this way, a nearby supernova could indirectly give birth to new stars and possibly new worlds that will one day host life. Astronomers have seen evidence of this in nebulae, where young stars cluster along the advancing front of a supernova remnant. In some cases, radioactive isotopes like aluminum-26 have been found in meteorites from our own solar system, hinting that the sun's birth cloud was enriched and perhaps triggered by a nearby explosion billions of years ago. Over time, repeated supernovae from massive stars in the same region carve out vast cavities in the galaxy's gas and dust, what astronomers call superbubbles. These cavities can span hundreds of light years, connected like cosmic soap bubbles in the galactic disk. Our own sun sits inside one, the local bubble, a region of hot, thin gas likely created by a series of supernovae over the last 10-20 million years. The Iron 60 found on Earth suggests that some of these explosions happened close enough to touch our world. In other words, we're already living inside the echo chamber of ancient stellar deaths. From a wider perspective, a supernova close to Earth is just one small node in a web of energy spreading across the galaxy. Each explosion sends out ripples that intersect with others, shaping the Milky Way's ecology, creating new stars here, erasing planets there, enriching the cosmic soup with heavy elements everywhere. In the short term, it's chaos. In the long term, it's evolution on a galactic scale. Without supernovae, there would be no gold in your jewelry, no uranium in reactors, no calcium in your bones. The same force that could end us is also the force that made us. That's the paradox of living in a galaxy. The very processes that build complexity also threaten it. For any civilization, human or alien, there's a ticking clock, a random countdown set by the life cycles of nearby stars. You can build cities, empires, even interstellar colonies. But sooner or later, a neighbor will explode. The only question is whether you'll be ready when it happens. You can't turn off a supernova. Once the core of a massive star collapses, the event is irreversible. The energy release is so immense that not even a civilization controlling entire planets could contain it. The only real question for humanity is whether we could shield ourselves from the consequences, or whether we'd have to flee. And that question forces us into territory where physics, engineering, and philosophy collide. In theory, we could try to protect Earth's surface from the incoming radiation. Large-scale shielding could take several forms: orbital sunshades or filters, massive arrays of thin, reflective material positioned between Earth and the incoming radiation. They would have to be precisely aligned and large enough to intercept much of the gamma and X-ray flux, and robust enough to survive the shockwave's debris. Artificial magnetic fields. Generating a powerful magnetic shield around Earth to deflect charged particles, similar to the natural magnetosphere but on steroids. This wouldn't stop gamma rays, but it could blunt the worst of the particle storm. Atmospheric chemical repair. Stockpiling ozone-producing compounds or deploying aerosols to offset ozone loss after the event. The scale required would be unprecedented planetary geoengineering on emergency timescales. Each option would require decades of preparation, trillions of dollars, and global cooperation. And they still might fail. If we can't protect the whole planet, we could protect parts of it at least temporarily. Deep, underground bunkers, submersible habitats, or shielded cavern cities could keep human populations alive through the years of elevated radiation and climate disruption that follow a nearby supernova. This would mean retreating into a long, controlled isolation, maintaining agriculture, industry, and society in sealed environments until surface conditions stabilized. It's a scenario that sounds like science fiction, until you remember that ancient life on Earth has survived cataclysms by going underground, hiding in caves, and living in the deep ocean. Another possibility is leaving Earth entirely, at least for the most vulnerable period. Lunar lava tubes, with their natural shielding from radiation, could serve as temporary refuges. Mars, despite its own thin atmosphere, might be safer from certain atmospheric chemistry effects simply because it has less ozone to lose. Further out, the moons of Jupiter and Saturn, shielded in part by their giant planets, could become lifeboats. But getting millions of people to these places on short notice is beyond our current capability. Evacuating an entire species, or even a fraction of it, is not just a transportation problem, it's a logistical, political, and ethical puzzle. Who gets to go? How are resources allocated? How do you maintain a functioning society in cramped, hostile environments for years or decades? History offers little comfort here. Even with months of warning, evacuations on Earth are messy and unequal. Scaling that up to planetary survival would test the very idea of civilization. The single most important factor in surviving a supernova is advance warning. If we knew centuries in advance which star was going to explode and when, humanity could build the necessary infrastructure, develop the technology, and perhaps even launch long-term interstellar missions to settle other star systems before the danger arrived. Without that time, our choices shrink rapidly. A century of warning becomes a scramble to build shielding. A year of warning becomes a global rush to shelter underground. Hours of warning? Then survival is a matter of pure luck. Even with decades to prepare, the greatest obstacle might not be physics but human nature. Investing in a defense against a threat that could be centuries away requires a level of foresight and cooperation that we rarely manage for problems just a decade ahead. Supernovae are rare enough that they feel like someone else's problem, but when they happen close enough, they are everyone's problem, everywhere, all at once. Right now, our species is at a unique moment in history. We have the technology to detect dangerous stars and to begin planning for planetary-scale emergencies, but we have not yet faced a supernova in the age of civilization. That means we're standing in a narrow window of opportunity, a time when the danger is real but the disaster hasn't yet arrived. We can choose to use this window to build a long-term survival strategy, or we can let it close and trust to luck. The news breaks quietly at first. A brief statement from an observatory, quickly repeated by astronomy blogs. Unusual activity detected in the red supergiant TYC 2000, 452 1031. Possible pre-supernova behavior. For most people, it's just another science headline. But astronomers know the truth. The star is only a few dozen light years away, and the signals are ominous. Changes in brightness, shifts in spectral lines, bursts of neutrinos hinting at instability. On social media, speculation begins. By nightfall, the words "close supernova trend worldwide." Snooze. The Supernova Early Warning System sends out a private alert to every major space agency. Neutrino counts are spiking. In the control rooms, scientists exchange tight-lipped looks. It could happen in weeks or hours. Governments begin quiet preparations. Power grids run stress tests, emergency stockpiles are opened. In the background, telecom providers brace for possible satellite disruptions. For the public, the only visible sign is a subtle one. The suspect star, faintly visible to the naked eye, seems slightly brighter than it was last week. It happens without warning. One moment, the night sky is as it has always been. The next, a point of light flares suddenly brighter than Venus, brighter than the moon, a white-hot flash that makes shadows dance in the middle of the night. Astronomers call it the shock breakout, when the explosion's shock wave reaches the surface of the star and releases its trapped light. To human eyes, it's as if a new sun has ignited in the wrong part of the sky. Birds start singing, confused by the sudden light. People spill into the streets, pointing, filming, staring. In every culture, every language, the same words rise. What is that? Normally, a bright meteor burns out in seconds, but this stays. The new star is still there, shining with a steady brilliance that turns night into a strange blue twilight. News networks scramble to cover it, cutting between telescopes and astonished onlookers. Scientists explain that the star is dozens of light years away, far too distant to ignite the atmosphere, but they don't mention the gamma rays and X-rays already racing toward Earth. In observatories, detectors register the incoming wave of high-energy photons. The countdown to the first atmospheric effects begins. The radiation reaches Earth. In the upper atmosphere, molecules shatter under the barrage, forming nitrogen oxides that begin tearing at the ozone layer. No one on the surface notices yet. The danger is invisible. In space, satellites detect sudden surges of static. Some systems reboot automatically, others fail. Astronauts aboard the International Space Station retreat to shielded modules, monitoring instruments nervously. The supernova has brightened even more, now casting sharp shadows at midnight. Astronomers estimate it will remain this bright for weeks, maybe months. Across the planet, people gather in parks, rooftops, and beaches to watch the sky. Some see it as beautiful. Others see it as an omen. Governments begin issuing UV safety warnings more out of caution than certainty, but scientists behind the scenes are already debating how much ozone will be lost and how quickly. Strange auroras ripple far from the poles, red curtains over deserts, green arcs above the tropics. Air travel is disrupted by radio interference. Some crops show signs of UV stress in just a few days, leaves curling under harsher light. In coastal towns, fishermen talk of strange water, fewer plankton blooms, subtle changes in the sea's surface. Marine biologists take samples and see early DNA damage under microscopes. By now, the second sun is a constant companion, dominating the night sky and competing with the moon. Children draw it in their schoolwork, artists paint it, musicians write songs about it. But the beauty hides the slow burn of change. UV levels climb, weather patterns wobble, and in quiet corners of the internet, people post charts and graphs showing atmospheric models with a curve that keeps bending downward. Somewhere in a deep bunker, a team of scientists begins calculating worst-case timelines. From the ground, nothing feels like a disaster, not yet. The second sun remains in the sky each night, a pale white lantern casting cold shadows across sleeping cities. But high above, in the stratosphere, the invisible work of the supernova's radiation continues. Atmospheric monitors detect a steady decline in ozone concentration. In some regions, UVB radiation at the surface has increased by 10%, enough to cause a measurable uptick in skin damage and eye problems. Farmers in sun-baked countries notice certain crops, lettuce, spinach, and some grains yellowing or failing altogether. In coastal labs, marine biologists report lower plankton counts. The chain reaction has begun. The ozone hole above Antarctica widens beyond any on record, spreading into mid-latitudes during peak sunlight months. Australia and South America see the earliest human health effects, higher rates of sunburn, even among people who avoid midday exposure. In the oceans, Plankton declines ripple upward. Sardine and anchovy catches drop sharply, sending fishing communities into crisis. Coral bleaching events intensify, not because of heat, but because increased UV disrupts the symbiotic algae corals depend on. Inland, schools begin holding classes indoors during the brightest hours. Public spaces post UV index warnings alongside weather reports. Meteorologists notice something else: changes in the jet stream. With less ozone to absorb ultraviolet light, the stratosphere cools. This shift alters wind patterns, moving storm tracks and changing rainfall distribution. The result is uneven and cruel. Some regions see catastrophic floods, others prolonged drought. Grain-growing belts in North America and Eurasia report mixed harvests, with yields down 15–20% in some areas. For wealthier nations, it's a hardship. For poorer ones, it's a crisis. Food prices rise globally, and political tensions simmer as countries begin hoarding supplies. From the streets of Cairo to the rice paddies of Vietnam, people adapt in small ways. Wide-brimmed hats become a staple. Cities experiment with UV filtering window films. Farmers plant UV-resistant crop varieties where possible. But for every adaptation, there's a breaking point. In equatorial regions, outdoor labor becomes dangerous for more of the year. Tourism in sun-soaked destinations collapses. Insurance companies quietly update their climate risk models to include stellar events. Not all life suffers. Some hardy plant species, naturally tolerant of high UV, spread into areas where competitors weaken. Insects with UV protective pigmentation see population booms. Certain algae flourish in the altered light spectrum, reshaping aquatic ecosystems. Even human industry finds opportunities. Demand for indoor farming technology, hydroponics, and climate-controlled greenhouses skyrockets. A few companies market second sun tours, taking visitors to remote areas where the supernova shines brightest. Months into the event, the human mind starts to bend around the new reality. The second sun becomes a constant backdrop, a fixture in art, advertising, and even politics. Conspiracy theories about its origin run wild. Some religious groups see it as a sign of the end times. Others call it a divine gift. But under the surface, anxiety spreads. Children grow up knowing this sky is not the normal one. Adults glance at the UV index each morning before stepping outside. And in research labs, the models for ozone recovery stretch further into the future than anyone had hoped. By the 1-year mark, global ozone levels have fallen by an average of 20%. Recovery is theoretically possible, but only if no further high-energy bursts arrive from the supernova. If they do, the damage could become semi-permanent. The climate, the oceans, and the biosphere have all shifted into a new equilibrium. Not stable, but survivable. The challenge now is whether humanity can keep this altered world functioning long enough for the sky to heal. The first burst of radiation from the supernova was the shock breakout, a flash of photons released when the blast reached the surface of the star. But a supernova is not a single event. It's a sequence of overlapping disasters, some unfolding over months, others over decades. About 14 months after the initial flash, Earth's magnetic field begins registering unusual disturbances. Solar observatories confirm it's not coming from our sun, it's coming from the remnants of the dying star. Charged particles, accelerated to near-light speed by the supernova's expanding shock front, have finally reached our solar system. Unlike gamma rays, these particles carry mass protons, electrons, and atomic nuclei, traveling fast enough to smash into atmospheric atoms and trigger cascades of secondary particles. The effect is twofold. Radiation exposure airplane crews on high-altitude polar routes receive doses far above safe levels. Airlines cancel certain flights indefinitely. Astronauts aboard the ISS and other orbital platforms must retreat into heavily shielded modules for weeks at a time. Atmospheric chemistry. The collisions create more nitrogen oxides, compounding the ozone depletion from the first wave. The models that once predicted recovery in a decade now push the timeline out by another 15 years. Electronics in space take the brunt of the storm. Microchips suffer single-event upsets, bit flips caused by particle strikes. Some satellites are knocked offline entirely. Others begin sending corrupted data back to Earth. The GPS network falters. Earth observation satellites crucial for weather forecasting drop offline one by one. The loss of orbital infrastructure forces humanity to rely on ground-based systems, slower and less precise. 18 months after the flash, telescopes pick up faint, fast-moving specks against the stars. These are the first fragments of solid material from the explosion, microscopic grains of dust, and the occasional pebble-sized particle, traveling at tens of kilometers per second. Most burn up harmlessly in Earth's atmosphere, producing an unusually high number of meteors in the night sky. But in orbit, even a speck of supernova debris is deadly. Several satellites are lost in impacts, and the International Space Station performs emergency maneuvers to avoid collision with tracked fragments. Each wave feeds into the next. Ozone depletion worsens UV damage to crops and ecosystems. Climate shift stress, water supplies, and agricultural systems already under strain. Satellite losses cripple the global coordination needed for disaster response. By the end of the second year, food prices have doubled again. Coastal cities in drought-stricken countries see mass migration inland. Governments declare states of emergency not for a single event, but for an ongoing sequence they can no longer call temporary. The supernova's second sun still blazes at night, though dimmer than in the first months. To some, it's a symbol of endurance proof. Humanity is still standing. To others, it's an unblinking reminder that the danger isn't over. Religions splinter, new ones form. In some countries, political movements call for abandoning damaged regions entirely and concentrating resources in lifeboat zones. Others push for rapid space colonization not as exploration but as evacuation. In a televised address watched by billions, an international coalition of scientists issues a sobering projection. If the aftershocks continue at the current rate, ozone recovery will take not decades, but centuries. Without intervention, Earth's surface will remain under elevated UV for multiple human lifetimes. The statement ends with a plea. Prepare for the long haul. The storm is not over. We must think in centuries, not years. 2.5 years after the first flash, humanity stops talking about waiting for recovery and starts building for survival. The Global Shield Initiative is born a coalition of space agencies, governments, and private companies with a singular goal: reduce surface UV radiation by at least 30% within a decade. The plan has 3 pillars. Stratospheric aerosol injection aircraft and balloons will disperse reflective particles high in the atmosphere to scatter sunlight and partially block UV. Orbital shade arrays thin, kilometer-wide films stationed at Lagrange points to intercept high-energy photons. Rapid expansion of indoor agriculture, scaling up hydroponics, aquaponics, and vertical farms to feed cities without relying on exposed farmland. For the first time since the event began, the public feels a flicker of hope. The price tag is astronomical. Trillions of dollars, decades of upkeep, and the cooperation of nations that, in some cases, barely speak to one another. But the alternative is worse. With ozone levels still 20% below pre-event norms and agricultural yields continuing to decline, the cost of inaction is measured not just in money, but in lives. Factories that once made consumer electronics now produce shade film by the kilometer. Aerospace companies pivot from tourism to freight launches for orbital shades. Nations redirect military budgets toward shielding and sheltering programs. By mid-year, the first orbital shade segments unfurl in space, their delicate silver surfaces gleaming in sunlight. Aerosol dispersion flights begin over the poles. In some cities, food grown in sealed skyscraper farms starts appearing in markets, a symbol of adaptation made real. The second sun in the night sky is noticeably dimmer now, fading toward the brightness of Jupiter. Astronomers confirm the visible light will continue to decline. Some dare to hope that the worst is behind us. Then, the neutrino detectors go off again. It's faint, but unmistakable. Another neutrino burst from the direction of the supernova remnant. This isn't supposed to happen. The main core collapse was years ago. Within hours, telescopes confirmed something extraordinary. The remnant's core has collapsed again, but this time into a neutron star unstable enough to produce a magnetar-level flare, a colossal release of gamma rays, more focused and potentially more dangerous than the original blast. Magnetar flares are rare, but when they happen, They can deliver more gamma-ray energy in a fraction of a second than our sun emits in 100 years. And this one is aimed almost directly at Earth. The projected arrival? 14 months from now. The implications are terrifying. All the shielding built so far is optimized for sustained radiation, not an instantaneous ultra-high energy pulse. The orbital shades won't survive the shock unless redesigned. The Global Shield Initiative scrambles to re-engineer its systems for a threat that will come in one blinding flash, with no second chance to prepare. News of the Magnetar flare reignites global tensions. Some nations argue for abandoning the orbital shade program and focusing entirely on underground shelters. Others push for massive lunar or Martian evacuation efforts. Conspiracy theories flourish claims that the flare is a cover story for secret weapons, that the second sun is artificial, that the event was engineered to cull the population. The fragile cooperation that held for 3 years begins to splinter. Astronomers begin releasing weekly updates on the Magnetar's progress. The date of arrival is circled in red on calendars worldwide. In schools, children calculate their ages when the flare will hit. Families quietly debate whether to move underground permanently. The second sun is almost gone now, its visible light no longer dominating the night, but the real danger is once again invisible, traveling toward us at the speed of light. The Magnetar flare's projected arrival date is fixed. No delays, no reprieves. Every model agrees. When it hits, the burst will last less than 2 seconds. But the dose of gamma rays will be unlike anything Earth has experienced in recorded history. The Global Shield Initiative shifts into overdrive. Orbital shades are redesigned to include sacrificial layers that will vaporize and absorb some of the flare's energy. Underground shelters, once built to protect from UV, are reinforced with dense materials, lead, water, regolith, to shield from the intense photon flood. Factories run 24/7. Launch schedules triple. Governments seize private aerospace capacity. The planet is now one giant project site. Weekly science updates become global events. Astronomers show simulations of the flare's impact on the upper atmosphere, ozone obliteration, chemical chaos, and temporary blinding of satellites. One diagram becomes iconic: a glowing wavefront striking Earth, followed by a haze of nitrogen oxides wrapping the planet like a bruise. It airs on every news network, every device, every language. The tone is clear. We will survive if we prepare. We will not survive if we delay. In Sao Paulo, a construction worker spends her days welding steel frames for an underground greenhouse that will feed 20 people after the flare. She jokes that she's building a farm for the end of the world. In rural India, families dig communal shelters beneath their villages, lining the walls with water barrels to block radiation. Children decorate them with bright murals of birds, forests, and suns the world they hope to return to. In Alaska, engineers convert old Cold War missile silos into emergency medical bunkers, stocking them with decades' worth of supplies. The second sun is gone now, faded back into the background stars. Night feels darker than it has in years, but also emptier, as if the sky itself is holding its breath. Telescopes show the expanding cloud of the original supernova faintly glowing in deep space. Behind it, invisible to human eyes, the Magnetar spins, winding up for the blast. A small gamma-ray flare from the Magnetar arrives, not the main burst, but a warning shot. Even at a fraction of the predicted energy, it fries several unshielded satellites and forces ISS crews to retreat to the most protected modules for 2 days. It's enough to prove the danger is real. Public opinion shifts overnight. Resistance to government mandates vanishes. In cities worldwide, people volunteer for shelter drills, practicing the 90-second evacuation from streets to safe zones. International travel halts. Airspace is cleared for final supply runs. Every launch window is used for shade segments, sensor satellites, and emergency beacons. Stock markets close indefinitely. Religious gatherings swell. In some places, music festivals and public celebrations are held, defiant acts of joy before the storm. The last update from the Global Shield Initiative is broadcast at sunset. Tomorrow at 14:16 UTC, the flare will arrive. Stay in shielded areas for at least 24 hours afterward. We cannot stop it, but we can. Shelters are silent, except for the hum of filtered air and the faint, rhythmic beeping of radiation monitors. In bunkers from New York to Nairobi, People grip each other's hands. In orbit, astronauts float in shielded modules, staring at countdown timers. In a data center in Geneva, the Global Shield Initiative's command network watches the flare's predicted arrival time tick down. Everyone is waiting for something they cannot see coming. The lunar surface, unprotected by atmosphere or magnetosphere, takes the first hit. The regolith flashes with X-rays, releasing a faint, invisible vapor into space. Sensors there relay the impact signature and then go dead. Gamma photons slam into Earth's magnetic field, distorting it like a shaken snow globe. Auroras erupt instantly at both poles, but these are not gentle curtains of light. They are blinding arcs of white and violet, stretching toward the equator. High above the ground, molecules of nitrogen and oxygen shatter under the burst. Nitrogen oxides bloom into existence, spreading like ink in water. In less than a heartbeat, the ozone layer's chemistry is altered on a planetary scale. Aircraft in flight experience sudden bursts of static cockpit instruments flashing with noise. Pilots drop to lower altitudes, hoping the denser air will shield them. Satellites outside low Earth orbit are blinded, their sensors overwhelmed. GPS systems go dark. Communications satellites cut out mid-sentence. In deep-sea cables, faint but measurable currents surge the electromagnetic pulse reaching into the infrastructure of the internet. Data centers isolate themselves, shutting down critical systems to avoid burnout. Alongside the photons, a secondary wave of ultra-relativistic particles arrives. They slam into the upper atmosphere, spawning showers of secondary particles that rain toward the surface. On the ground, most people feel nothing. The atmosphere absorbs most of the lethal energy, but at high altitudes, aircraft crews and mountain observatories receive radiation doses equivalent to years of normal exposure in a single instant. In the upper atmosphere, air molecules fluoresce under the incoming energy, producing a faint, ghostly blue glow. In the shelters, some people notice the light seeping under doors or through ventilation shafts, as if the sky itself is pulsing. And then, silence. The gamma-ray burst has moved on, racing toward more distant stars. The damage it has done here is invisible to the naked eye, but it is deep, chemical, and global. In those 2 seconds, the ozone layer has taken a hit worse than the first supernova flash. Satellites in medium and high orbits are permanently crippled. The magnetosphere is ringing with disturbances that will take weeks to settle. Shelters receive confirmation from ground-based observatories. The flare is over. Radiation levels at the surface are safe for now. But atmospheric models show that ozone recovery timelines have been pushed not just decades, but possibly centuries into the future. People emerge cautiously into daylight. The sun looks the same, but the air feels subtly sharper. Astronomers warn that UV levels will spike as soon as the polar air currents redistribute the chemical damage. The flare was short, but the shadow it casts will be long. The first thing scientists notice after the flare isn't visible to the naked eye. UV measurements from ground stations spike to unprecedented levels. Even in polar winter, the readings are higher than anything in the satellite era. The ozone layer has taken a catastrophic hit. Atmospheric chemistry models show 40% depletion in some regions, with recovery times stretching into centuries unless active intervention is maintained indefinitely. Governments immediately reimpose strict daylight exposure limits in equatorial and mid-latitude regions. Outdoor work shifts to early morning and late evening. Schools run on nocturnal schedules in the worst affected zones. Architects rush to retrofit cities with UV filtering materials. Entire streets are covered with translucent canopies that block harmful wavelengths while letting in enough light for plants and people to function. Glass production booms. Polycarbonate domes rise over marketplaces, sports arenas, and public squares. Parks are reimagined as light gardens, using filtered panels to create safe sunlight zones. Urban skylines change in months, not years. The open-air city becomes a relic. Outdoor agriculture becomes a regional lottery. In some high-latitude areas, crops still grow under modified schedules and UV protective films. Closer to the equator, farming shifts almost entirely indoors. Massive hydroponic facilities spring up in abandoned malls, warehouses, and purpose-built skyscraper farms. The glow of LED grow lights becomes a common sight in urban cores. Rural communities either adapt with enclosed greenhouses or relocate to areas where the air and sunlight are less dangerous. Entire valleys in northern climates are repurposed for food production, guarded as strategic assets. With many high-orbit satellites lost in the flare, Earth's digital infrastructure has to be rebuilt. Instead of replacing everything in the same orbits, engineers deploy low-orbit swarms of smaller, shielded satellites easier to protect and replace. Global communications are slower and patchier in the transition, leading to a world that feels both more connected through shared struggle and more isolated by technological bottlenecks. A generation that grew up under open skies now lives under filtered light. Festivals are held at night, workdays are timed to avoid direct sun. Fashion trends turn toward layered UV-resistant fabrics, reflective hats, and face shields that double as style statements. Outdoor sports move indoors. Architecture merges with agriculture in vast biodomes that blur the line between park and farm. Cities smell different, less of open air, more of climate-controlled interiors. Religions reinterpret the event. Some faiths treat the magnetar flare as a trial humanity has passed. Others see it as the moment the age of nature ended and the age of shelter began. The Global Shield Initiative, originally meant as a decade-long emergency program, becomes a permanent arm of human civilization. Its orbital shades and aerosol injections are now considered basic planetary maintenance. New generations will grow up never having known an unfiltered sky, and for many, the idea of natural sunlight will be as abstract as the dinosaurs, something that once existed, but no one alive remembers. 10 years after the magnetar flare, the ozone layer remains thinned. UV levels at midday are still dangerously high, though manageable under the global shield network. In the oceans, plankton communities have shifted towards species with thickened cell walls or special UV-blocking pigments. These survivors form the base of a changed food web. Some fisheries recover with different target species, others collapse entirely. On land, plant life shows similar shifts, more waxy leaves, deeper root systems, and altered flowering times. The forests that regrow in damaged areas are denser, darker, and filled with plants that filter or block light before it reaches the ground. Animal life responds in subtle but measurable ways. Insects, reptiles, and amphibians show increased pigmentation, darker shells, and protective scales. Some migratory birds shift their routes toward higher latitudes, where the shielded zones are more extensive and the air is less UV heavy. Mammals, including humans, develop slightly thicker skin and stronger melanin responses over generations in areas with chronic high UV. Public health officials still enforce protection measures, but the baseline biology of life on Earth is slowly changing. 100 years after the flare, Earth's cities are sealed ecosystems. What was once urban life has become a network of enclosed biomes connected by shielded transport tubes. Rural farming exists only in extreme latitudes or under protective domes. Wildlife survives mostly in northern and southern refuges, where human intervention maintains lower UV levels. The equatorial belt has become a zone of engineered ecosystems, forests planted with UV-resistant species, animals relocated to artificial reserves. The orbital shield arrays are now as essential as the moon in the night sky, permanent symbols of a planet maintaining its own habitability. The descendants of today's life forms are unrecognizable in detail. Fish that once relied on plankton now feed on tough, pigmented algae. Forests have developed multiple canopy layers to block UV before it reaches the understory. Humanity itself has split into several cultural and biological branches. Open sky populations genetically engineered for higher UV tolerance, living in partially shielded rural zones. Enclosed citizens living entirely indoors, paler and more dependent on artificial light cycles. Off-world colonies, adapting to lunar and Martian environments, genetically and culturally diverging from Earth-bound humans. The planet is stable, but it is no longer the same world that existed before the supernova. From the vantage of deep time, the magnetar flare becomes a geological marker. Layers of rock preserve the isotopes created by the radiation burst. The pollen records show a sudden shift in plant species, and fossil assemblages tell the story of an extinction that was partial, selective, and transformative. If some future civilization studies Earth millions of years from now, they will see this as a singular moment, a fork in the road where one star's death rewrote the evolutionary script of an entire planet. Centuries after the flare, the supernova's debris cloud is still growing. It no longer looks like a violent wound in the sky. Instead, telescopes see an enormous, delicate bubble of gas and dust, glowing faintly in the light of surrounding stars. It stretches for dozens of light years, moving outward at thousands of kilometers per second. Inside it are the raw materials forged in the heart of the dying star: iron, nickel, gold, uranium, and dozens of other heavy elements that never existed in the universe before the explosion. Every grain, every atom of these elements was born in that star's final moments, scattered into space like seeds in a cosmic wind. Most of the debris will drift forever, pulled into no particular destination. But some fragments will encounter clouds of interstellar gas, the same kind that once gave birth to the supernova's progenitor. When a fast-moving shockwave collides with a cold molecular cloud, something remarkable happens. The gas compresses, gravity takes hold, and new stars begin to form. This is the galaxy's recycling program, the death of one star catalyzing the birth of dozens more. Even as humanity rebuilds beneath orbital shades, the supernova's shockwave is quietly writing the opening chapters of other planetary stories far beyond our reach. Astronomers already track the leading edge of the debris wave as it approaches nearby dark nebulae. In a few 100,000 years, those nebulae will ignite into clusters of bright, young stars, surrounded by disks of dust and gas, the raw material for planets. The dust from our supernova will mix into those disks, becoming part of the rocky crusts of future worlds, the metallic cores of their planets, and perhaps the biochemistry of life itself. For humanity's descendants, whether on Earth, Mars, the Moon, or deeper in space, the supernova's remnant may become a place of pilgrimage, not out of fear, as in the days of the flare, but out of curiosity and connection. Imagine a starship arriving at the heart of the fated nebula millions of years from now. Its crew, genetically and culturally distant from us, yet bound by the same origin, gathers samples of ancient dust. They study the isotopes, trace them to the year the second sun rose in Earth's skies, and realize that their own worlds contain fragments of that very event. The supernova would no longer be just a disaster in history, it would be part of their material heritage. From an even wider perspective, our supernova is just one node in a vast chain of stellar life cycles across the Milky Way. Dozens of such explosions happen every millennium, each carving out bubbles, each sending shockwaves into the surrounding medium. Together, they weave the chemical tapestry that makes complex worlds possible. Without them, the galaxy would still be hydrogen and helium. No planets, no oceans, no biology. It is a paradox so grand, it's almost difficult to hold in your mind. The same process that nearly ended life on Earth is the process that made life possible here in the first place. If another intelligent species on some distant planet one day studies its own geological history, they might find traces of our supernova in their rocks, a thin layer rich in certain isotopes, deposited at the time the debris wave passed through their system. They might wonder where those atoms came from. They might build telescopes, trace the path backward through the galaxy, and realize it began at a small yellow star in the Orion Arm, a star that once had a planet covered in domes and shields, recovering from the very event they are now studying. In this way, the supernova is not an ending, but a handoff. The elements it scattered will find new homes. Some will end up buried in the crusts of lifeless worlds.
Some will swirl into the atmospheres of gas giants, and some may become part of the proteins and DNA of beings we cannot yet imagine.
And those beings, whether they look up at their sky with eyes, antennae, or something stranger, might one day tell their own version of this story, a story of how a star's death gave them the chance to exist. 5 centuries after the magnetar flare, Earth's skies are still not what they once were. The ozone layer, while thicker than in the immediate aftermath, remains a patchwork shield, its integrity maintained by ongoing human intervention, a combination of stratospheric aerosols, orbital shade networks, and active atmospheric chemistry management. Generations have been born and died under filtered skies. For them, the age of open sunlight is a legend, preserved in old images and fragments of pre-event culture. Many view it with nostalgia, others see it as reckless, a time when humanity walked unprotected beneath a dangerous universe. The equatorial belt, once a scorched and UV-blasted zone, is habitable again, not through natural recovery alone, but because human engineering has learned to bend sunlight itself. Vast light harvesting arrays float in high orbit, capturing unfiltered solar radiation and re-emitting it at safer wavelengths through atmospheric projectors. The result? Daylight that is warm, bright, and harmless to skin and DNA, bathing once abandoned lands in a glow that is technically artificial, but psychologically healing. Cities rise where jungles once stood, their architecture blending old-world openness with subtle protective curves and coatings. Agriculture moves outdoors again, though always with quiet vigilance. Above Earth, the orbital shades' once emergency structures have been rebuilt into a permanent ring of interconnected habitats, observatories, and shield stations. Seen from the ground at twilight, they trace a faint band across the sky, shimmering like a crown of silver threads. They serve as both shield and symbol, a reminder that planetary defense is not optional in a galaxy where stellar death is inevitable. Humanity no longer assumes safety from the stars. It plans for them. The planetary population has shifted. Many of the great megacities of the 21st century are gone or reduced, replaced by distributed clusters of medium-sized settlements linked by high-speed ground tunnels and airships designed for minimal UV exposure. Some groups remain committed to fully enclosed living domed arcologies, where weather, light, and climate are entirely human-controlled. Others embrace a reopened world philosophy, pushing to live as close to pre-event conditions as possible, even if it means accepting higher environmental risks. Tension exists between these philosophies, but it is more cultural than hostile. The shared memory of surviving the flare binds humanity together far more than it divides it. By now, off-world colonies are not outposts, they are thriving societies in their own right. The Moon's lava tube cities, Mars's shielded canyons, and asteroid mining hubs all trace their origins back to the supernova era, when humanity first realized it could not rely on a single planet. The colonies see themselves not as Earth's satellites, but as partners in a shared civilization. Trade flows both ways: rare metals from the belt for Earth's industry, agricultural and genetic diversity from Earth for the colony's closed ecosystems. And together, they maintain the Stellar Hazard Network, a chain of telescopes, particle detectors, and deep space probes scanning for the next dangerous star. Over centuries, the magnetar flare has shifted humanity's sense of time. Civilizations now think in geological and astronomical scales. A short-term plan might cover a century. A long-term vision could span 1,000 years. Art and literature of this era often portray humanity as a caretaker species, not just of Earth, but of worlds yet to form, stars yet to shine. The idea that we are made of dead stars is no longer a poetic metaphor, but a lived truth. Even with the world stable and the species thriving across multiple planets, one question lingers: how will the story of the flare be told to the far future? Some argue for recording it as a warning, a reminder that survival is never guaranteed. Others see it as an origin myth, the moment humanity grew up and took its place among the galaxy's enduring civilizations. In the archives beneath the orbital crown, there is a vault containing the full record, from the first news of the dying star to the final completion of Earth's shield. It is designed to last for millions of years, in case our descendants or strangers from another world ever need to know how we faced the death of a neighbor star. It has been 7 centuries since the second sun burned over Earth. The magnetar flare is long gone, its energy scattered into the void, but the expanding debris cloud of the original supernova still drifts through the Orion Arm, a shimmering nebula of dust, gas, and heavy elements. The ship Aurora's Wake is the first crewed vessel to visit it. Her crew is a mix of Earth-born scientists, Martian engineers, and asteroid belt navigators, the living proof that humanity's home is no longer a single planet. Their mission: to take samples, map the cloud's composition, and confirm how much of it bears the isotopic fingerprints of the blast that once altered Earth's history. Day 12, since departure from the Ceres Gate. We've crossed into the leading edge of the cloud. To the eye, it's faint, a pale shimmer against the starfield, but on instruments, it's alive. The spectrometers show every color the human eye can't see, and the particle counters are singing like storm chimes. I try to imagine what this dust was before the heart of a star, heavier than anything for billions of kilometers, torn apart in seconds, and now it drifts, waiting to be part of something new. From the bridge, the crew sees great filaments of gas stretching like cosmic rivers, illuminated by the ship's lights. The colors shift in slow, ghostly gradients: crimson hydrogen veils, blue-green oxygen wisps, golden traces of sulfur. Chunks of denser material, ancient clumps of nickel iron, frozen carbon compounds drift in loose swarms. Each is tagged by the ship's AI for sampling. Some of the larger masses spin slowly, faintly glowing from residual radioactive decay. We've confirmed isotope ratios matching the layers found in the flare-era geological strata on Earth. These are the same atoms that once streamed past our planet at near light speed. I'm holding a container of dust that, 700 years ago, could have killed me in seconds. But here, in the cold of interstellar space, it's harmless, even beautiful. And it will one day be soil, mountains, perhaps the bones of creatures that haven't yet evolved. Deeper in, the gas density increases. The ship's shields flicker as they pass through knots of charged particles. Instruments detect a compact object far ahead, the neutron star that remains of the progenitor. It is small, only about 20 kilometers across, but its magnetic field is still powerful enough to distort the ship's sensors. The crew observes it from a safe distance, a dark sphere rimmed with faint X-ray light, spinning silently in the void. This is the corpse of the star that once threatened Earth, the quiet heart of an event that changed the course of human history. Seeing it here, it's hard to believe this thing nearly ended our world. It doesn't roar or rage, it just turns, slowly, endlessly. We've left an offering in orbit, a capsule with records of our species, our worlds, and the flare that tied us to this place. I like to think that if someone else finds it, they'll understand the connection. The mission's final days are spent collecting core samples from the denser knots of dust. Some will go to laboratories on Earth and Mars. Others will be set aside for seeding planetary engineering projects, ensuring that the metals and minerals forged in this supernova will one day help shape new biospheres. In doing so, the crew closes the loop, taking matter that once endangered life and deliberately using it to create the conditions for life elsewhere. As Aurora's wake leaves the remnant, the crew watches the filaments fade into the distance. The cloud will continue to expand for millions of years, eventually blending into the wider galactic medium. Humanity will not be here to see it vanish, but its story will be recorded, carried in archives on Earth, Mars, the Moon, and beyond. The Aurora's wake comes back through the Ceres gate, its hull still faintly dusted with particles from the remnant. The samples it carries are priceless, not for their rarity, but for what they mean. These atoms were once part of a star, born billions of years ago in another corner of the galaxy. For most of their existence, they were locked deep inside that furnace, until a final, unstoppable collapse cast them into space. Some streamed past Earth as deadly light, some rained down as debris, and some drifted for centuries before being gathered by human hands. For the first time, we have touched the source of our own near extinction and found it to be the same source of our creation. Life on Earth exists because of supernovae. The iron in our blood, the calcium in our bones, the oxygen we breathe, all forged in ancient stellar explosions long before our sun was born. Without them, our planet would be barren rock or swirling gas. And yet, the same process that made us possible nearly erased us. When the second sun lit our skies, when the magnetar flare washed across our atmosphere, we saw the destructive face of the same cosmic cycle that built the ingredients for life. It is a truth as old as the stars. Creation and destruction are not opposites here. They are stages of the same process. In the centuries after the flare, we learned to protect ourselves. We turned cities into living shields, built a permanent orbital defense, and spread to other worlds. But we also changed in ways that cannot be undone. The idea of an open sky became rare, almost ceremonial. We learned that the universe is not a static backdrop, but a living system, one in which danger can arrive without warning, carried on light that has been traveling for years. The Planetary Shield Network is now a symbol of that awareness. It does not just guard against the last supernova, it stands ready for the next. Long after our memory of the flare fades into legend, The evidence will remain in the rocks, in the ice, in the altered DNA of every surviving species. The magnetar flare will be a boundary in Earth's biological record, a moment when life's trajectory shifted. Perhaps, millions of years from now, another intelligence will study those layers and wonder what happened. They will see the sudden chemical changes, the extinction of certain species, the rise of others, and if they are able to trace it back far enough, they will find the remains of the neutron star, and maybe, just maybe, the records we left there. We are not alone in this experience. Across the Milky Way, other civilizations, if they exist, have surely faced their own stellar catastrophes. Some may have perished. Others may have adapted, as we did. A few might have turned such moments into opportunities, carrying the seeds of destroyed worlds to plant new ones. And somewhere, perhaps right now, the debris of our supernova is falling into a forming planet's atmosphere, mixing into its oceans, becoming part of the chemistry of life. In time, those beings, whoever and whatever they are, might look up at their own stars and wonder where they came from. From the surface of Earth, the night sky looks peaceful again. The second sun is gone. The remnant of the supernova is invisible to the naked eye, just another patch of blackness among billions. But we know better now. Every point of light is a story in motion. Every star is both a promise and a threat. Every atom in our bodies has traveled across cosmic distances and survived unimaginable violence to be here in this moment. We are made of star death. We are proof that the universe's most destructive forces can also give rise to thought, art, and love. If a star exploded next to Earth again, it could end us. But it could also begin something new, not just here, but light years away, in worlds we will never see. That is the cycle we live in, whether we accept it or not. The truth is simple and impossible all at once. We are temporary. The universe is forever. And in the vast exchange between life and death, creation and destruction, we are not just spectators. We are participants. So we look up, knowing the danger, knowing the beauty, and we keep building, keep exploring, keep leaving something behind. Because one day, somewhere, someone else may stand under their own sky and realize that they, too, were born from the ashes of a star.